Okay, so yeah, for this week's nurse night, I basically prepared two things. So first there is there is like a cool math trick that I want to show you. Well, of course, every triangle is isosceles is not really a correct statement, of course, but maybe the proof will surprise you. And then there is the system, that system that I put as a nurse night that the company sold. So I also decided to put this here. Actually, we might want to start with this one, with the second one, because it's it's really much quicker to go through. So yeah, going directly to this was the original problem statement. Right. I think, David, you had some decent tries at it, if I remember correctly. Is that right?
Yep.
But they didn't quite get it in the end, right? So yeah, I think this should be beneficial to all of us, I guess, if you're curious how to solve it. Okay, so having this, how would one go about solving this system, right? Because I mean, it's not really that much. We have three variables and two relations. So in theory, that is not enough to solve the system, but without any tricks. But thankfully, there are some tricks that can work here. So what does the first relation tell us? When something when a sum of three variables like equals to 3 and they are all positive, that means we must have at least one that is greater than 1, right? And what do we know about numbers that are greater than 1? When you power them up, that they become bigger. So the intuition here is what I'm trying to say is that this quantity here, the sum with power 7, should be greater than the other one with power 6 with power 5. Because the quantity that is higher than 1 will, let's say, overpower the ones that are less than 1, because the ones that are less than 1 are going to become even smaller than the ones that are, that are power 5. Yeah. So that's basically the intention. I want to demonstrate that this quantity in the left is greater than this quantity in the right, and the equality happens just when all the numbers are equal. And of course, when all the numbers are equal, the only solution is 1. So how do we do that? Well, there are two basically solutions. The first one is just finding out that this inequality is satisfied. Here is just, we don't really need this. I mean, yes, the system is symmetric, and we can basically assume an order. And yeah, I just went for commodity here, x greater than y and greater than z. And yeah, we have this obviously because x is greater than y, they are both positive. So when you put them at an odd power, the order still remains. So why this? Well, we have 5 and 2 in the problem statement. So 5 plus 2 equals 7. So that's basically why I did this. Of course, we have this odd-looking LHS, or RHS, so right-hand side. So we kind of need to get rid of this or use some some simplifications, some tricks. So yeah, if we just wrote everything here and sum them up with this relation as well, this I put because, as you can see, if you just look at the power 5 of x here, so we have this term, x power 5, y power 2, and then we have this term, x power 5, z power 2. Then it would be ideal to also have an x at power 7, because then we can just take x power 5 out and we can get the sum that we want, which is basically this one. And basically, yeah, after we got this, it's all over, because we got in the problem statement that the sum of x to cyclic sum equals to 3. So we got the inequality that we want to prove. And of course, if here if we force equality, that means here we also have equality on each one of these. So that means all numbers shall be the same, and it's over. So yeah, not really a very fancy solution, basically just multiplications. But yeah, it's quite tricky. I mean, if you don't see this, then yeah, it is quite difficult, I guess. There is, of course, a one-liner solution, which is just using the Chebyshev inequality. So that's why I wrote that order. So I established a particular order at first so that we can use Chebyshev here. And this, it uses the fact that, again, x power 2 and x power 5, if you multiply those, you get x power 7. And you get this inequality like directly without any trick. So that was basically it for this problem. What do you think, David? Do you think you're closer than you thought beforehand? What do you think of this problem?
I mean, yeah, no, it's pretty elegant.
Yes, of course, I like the non-Chebyshev inequality solution more because it just uses basic techniques. But yeah, it would be quite difficult, I guess, to see this, which just solves it. But yeah.
Aren't you supposed to show the only solution is 1? I thought that was the task.
What?
I thought the task was to show the only solution is everything is equal to 1.
Yes.
So how does this inequality show that? The Chebyshev one?
So it helps because if in general this is this quantity is greater than this one, but in the problem statement we know we are forced we force it to be equal. That means we also have equality here, and that means the equality happens only when all the numbers are the same. So that means it's just one solution when all the numbers are the same. And because they are positive, there is just only one solution when all the numbers are the same, which is 1. That's basically it.
You don't need to show like additionally that 1 is the only valid solution there, even if it's like obvious from our sampling.
So if you assume that if there are other solutions, then we'll have strict inequality here. So the sum of x power 5 will be less strictly than x power 7, which contradicts the problem statement, right?
Yeah, so don't you still need to do just like case if like they're not equal to each other, then blank and then by symmetry or something? So it seems like you still need like one more line.
Yeah, sure, I guess. I mean, not for Chebyshev though. Oops, because here you just directly have this, and you know from Chebyshev that you just have one solution in terms of equality. It is given here in the theory. I think I haven't put it here, but yeah, that's basically when equality happens in Chebyshev. But yeah, I guess you can. You technically also need to just put this line here, right? You still need to assume the order, I guess. So I mean, of course, this is like the only line that, I mean, it has like that solves the problem. But sure, you kind of need like 2 extra lines just to be rigorous to get the max score, I guess, in a competition. You can't just put it here, put this here and solve it. Although it is like the 99% of the solution. Right. I guess we can move to the proof that every triangle is isosceles. Yes. So I put some background here just to we do need this in the proof. So I mean, maybe you remember from geometry classes. So angle bisector, pretty straightforward, right? You have a line that base separates like halves an angle in 2. So yeah, these 2 are equal. That's basically all you need to know. And this is how it looks in a triangle. And then the perpendicular bisector. So you have like a segment A1, A3 here, and the perpendicular bisector is just a line that's perpendicular on the middle of the segment. And what we need to know here is that every point on this perpendicular bisector is at equal length to the sides of the segment. You can see my cursor, right? So OA1
Yeah.
equals OA3. Yeah. And that's basically the only property that we need. And then finally, yeah, some congruence between triangles, right triangles. So if you have the hypotenuse, I think that's what it's called. Maybe my pronunciation is not great. And an angle. So if you have these two into triangles, then that means they are congruent. So it means they are exactly the same triangles. And yeah, if you have like a side, a leg, I think it's called a leg, and the hypotenuse the same, then again these triangles are the same. So yeah, let's see how we use this. So I have to open the, where is this? Yeah, so yeah. So I have this, but let me open in Paint 3D. Okay, I do this open. Can I open this? Okay. Right, so we have this triangle. It's a random triangle, and I'm gonna show that it's isosceles, although this side is obviously smaller than this one, but I'm still gonna show that they are the same, right? So let me just denote this, right? So we have A, let's put B here, and let's put C here. Okay, so what I did here, I take the bisector of angle A, right? So that is basically the first step. Take bisector of angle A. So that means we have basically this angle equals this one, right? What do we do now? We take the perpendicular bisector of BC. So that is perpendicular bisector of BC, right? Which is this. Let's put an M here for middle, I guess. And then we want to consider, consider the intersection between these two lines. So yeah, let's just taking things easy. That's why I wrote them like this. So let's mark this as O. So this is point O, M, C, B, A, and of course it's being like the perpendicular bisector. That means here we have like a 90-degree angle, right? And also this segment is equal to this segment. Now we need to so take the line BO and OC. So let's just draw them, I guess. Take like this, B, K, and this. Good. So what do we know about perpendicular bisector? We will have that we will have BO equals OC, right? So that's what we learned from the background. Let's mark it here as 4. And also I'm gonna mark them as like a two small lines here. So we have BO equals OC because this is a perpendicular bisector, right? Good. So this is basically the setup. We just have to draw one more thing. So from this point O, we need to take the perpendicular to the other side. So AB and AC. And it's just the perpendicular, not the perpendicular bisector. So just from this point O, I'm just gonna draw the perpendicular to AC. So kind of like, where is this? 2D shapes. Okay. So kind of like this, I guess it's 90 degrees, right? So I'm gonna put it like this. Let's mark it as 90 degrees. And let's do the same for AB. It seems about right, I guess. Again, mark it as 90 degrees. And of course, let's run here in the steps. So take perpendicular from O to AB and AC. But let's mark this as let's put like an X here and Y here, just so that all the points are are denoted. Yeah. So what do we do now? Let's look at the triangle AOX and AOY. So we have AOX equals AOY. Why? Because we have AO equals AO, right? So we have the hypotenuse the same, and we have the same angle, right? We have XAO equals angle YAO. So if we go back to the where is this? The congruence, yeah. So it's basically this one, the first lemma, I guess we can put it. So this is totally legit, as you can see. Hypotenuse the same and one angle the same. This one is also the same because it's be 90 degrees minus this one, so it works out. So we have AOX equals AOY. So that means this. This means that the triangles are congruent, so the same, which means we will have these particular sides to be equal. And also these ones, right? Because they are congruent. Good. Now we need to look at the other triangles, XBO and YOC. So that means, yeah, my claim is that XBO equals YOC because we have the same hypotenuse and the same leg here. And again, if you look back at the second lemma, if the hypotenuse is the same and one leg is the same, then the triangles are congruent. So let's write this here. So because XO equals YO and BO equals OC. So what does this mean? This means that we also have these the same, which means this one is equal to this one for every triangle. And yeah, that's basically the proof. And it's over. So what do you think?
Is it XBO equals to YOC or YCO?
XBO, YOC. It is this is correct, I think. XBO YOC. Yep. Because here you can take XB and YO. Oh wait. So it's yeah. Well, it's okay. The order is like this XOB. It still doesn't change the
Yeah,
aftermath,
yeah,
but yes. YOC like this, right? Yeah. So that's the congruence because XO equals OC, right? And BO like this. So OB equals OC. This is given, right? And you also have XO equals YO. Yeah, but from this congruence, you can get XB equals YC, right? You still get this.
Yeah.
So yeah, so from this, yes, every triangle is isosceles, and you can't prove me otherwise, can you? What does the audience think? Eh? Is there a flaw in my proof?
I mean, all looks legit, but yeah, you sneaked something in between.
What is that? What do you think?
I don't know.
Well, I guess it was proven then, right?
So far, yes.
I'm glad that we have established that. David or Johnny, what do you think of this? Where is the flaw?
Isn't isosceles every side is the same length? That's the definition, right?
Yep. So,
So
I just
I-
drew a random triangle and I showed that AB equals AC for every triangle.
I think that's when.
Yeah, but
two
you didn't
sides
show
are
that
equal.
BC is equal to either one.
Which one?
Don't you have to show that BC is also the same length as
That's
AB and
equilateral.
BC?
That's equilateral though.
Well, I was just asking, like, isosceles I thought was every triangle
Ah.
has the same length, and you said yes.
Yes, so you can show that AC equals BC, doing the same thing, but taking the intersection from so taking the intersection from the bisector of C and the perpendicular bisector of B. It's the same thing. Here I did it for A, but for example, I can take the bisector from C and the mediator from B, and it's the same.
Oh yeah, isosceles is just two mash up.
Yeah. I just wanted these particular sides, but you can do it for AC and BC as well, just different intersection.
Aren't you assuming that the center lies inside the triangle?
That is one assumption.
It's definitely not for every triangle here. But if it
Why
is,
do you think that, David?
no, I mean you can just easily construct one where the center is outside the triangle.
You can, but I mean here it's pretty legit, right? Look at the
Yeah,
drawing.
yeah. So for this one, I'm not quite sure what the flaw is.
Like it does lie inside, right? Like, and this is clearly bigger than this one.
I mean, yeah, it just I'm a bit confused at really like the first step. Like why exactly is the intersection?
We can try on another one.
The
I guess.
bisector, like, yeah, it just seems a bit weird now. To me, for different triangles, it would be either like inside or outside of the triangle, no? And then
Yes.
there would be some weird stuff because new triangles come out. I don't know, maybe I'm wrong, but
Yeah. So
yeah, I mean,
we can try like
that
brand new. So I'm gonna make it like a bit more obvious, right? With this. This is a lot bigger, right? And we just do the same thing, yeah? Kind of like this.
yeah, but maybe can you do it on like a triangle that's like obviously not like really like I don't know okay, I cannot draw here, but let's see.
But how do you know now that you have split the angle like precisely in half? I'm not sure. yet.
It's about right. So it's legit the same thing, right? You do this and you have these triangles congruent and these ones congruent, and then you have yeah, basically this one.
Yeah. So there's clearly something in the proof that breaks when you say with the second set of triangles when you say that those are congruent. There's something in the
These
assumption.
ones.
Yeah.
These ones.
Uh,
Well, yes, but I mean, well, exactly, because we know these are the same, right? Because this is the perpendicular bisector, and we know here we have 90 degrees, right? And we know these are the same because these ones are congruent.
Yeah, I'm pretty sure it's
So-
literally like in the it's probably like the whole foundation of this, like there's probably like one flow. I mean, that's probably why you're asking us, right? Which means that the rest like completely like bases the whole conclusion on on the foundation of this thing, which is like the intersection at the beginning, which means that you can prove a lot of different things, right? Like which means that if the basis is wrong, then then like you can prove anything you want, right?
Yeah, but that's
Otherwise,
what I'm
like,
asking. Where is the mistake that I did?
I
Because
that's what I'm saying. I
But,
don't know.
Tidor, like obviously the lines that have like two lines on them is not in the middle, not necessarily in the middle of each triangle, right?
yeah,
yeah,
are you referring to these two
Yeah, these are obviously not like directly in the middle. So
directly? Okay, so you said that there may be outside.
Yeah, that's what I was saying earlier. Like it in some triangles, I'm pretty sure like
Okay, so
you have to
then
go
let's
outside of the
take.
triangle, and some of them it can
Yeah,
be
you're
inside.
referring to the perpendicular side. Okay, let's see. So I guess let's take a very weird triangle, I guess. But what I'm saying is, if you have a point, any point inside the triangle, oh my, I drew it like equilateral. If you have any point inside a triangle, the perpendicular from that point to these sides will always be like inside the triangle. That's what I'm saying. So if you have like any point here, like anywhere, even here, everything is like inside, right?
yeah, that does make sense. It is always inside, actually.
It is always inside, see?
So what's the SparkNotes again? How we got here? So why do the two hashes exist? Like how are those two congruent?
Okay, so these two are the same between this, because this is the perpendicular bisector of the triangle, of the segment, of this segment. So
Okay.
these two are the same. That's the
Okay.
property.
Yep.
And then these two are the same because you have, remember I took the bisector. So you have this angle equals this angle and you have the same hypotenuse. So that means these triangles are congruent. So that means these two are, again, these two. So that means these ones are congruent. So this side will be equal to this side.
Yeah, I didn't get that last part. So you're saying the angles on the top are like opposite of the single hash. So therefore,
These triangles from the top.
yeah, the two angles on the top, yeah, those two
Yeah,
are adjacent
I
to the
mean,
single.
you can see like the same angle, right? And the same hypotenuse. So you have same hypotenuse, same angle, that means they are congruent. According to, this. Same angle, same hypotenuse.
Okay, but does the angle at the bottom also have to be the same?
So
Like that one, yeah, where your
from
cursor
the
is now?
button, for the button, we are not looking at angles because here we obviously just have this right angle. For these two, we are just looking at the hypotenuse, which is the same, and a leg of the right triangle, and this is the leg that are the same. So it's a different type of congruence that we are using here for these two to be the same. And these two are the same because these two are congruent. Something that we established.
So yeah, the second length, can you go through that one again, like even slower for the
Yeah.
slow ones in the audience?
It's okay.
The like after you've proven that the second set of triangles are the same, prove that the lengths below those second set of triangles are also the same.
Okay. Oh, that's weird. I think I should have saved that. Oh. What's this? Is this? Right. So this. Only for you, David. I'm gonna do it again. Look at this. A, B, C, right? A, B, C, this is M from middle, and this is O. Right? I'm gonna mark this as the same because it's the. I'm gonna write it here.
Yeah, so everything up to the second set of triangles, that's fine. Just
Yeah.
the final bit of proving that like the you have some bisector between A and B, and
Yes.
you prove that the bisector is I mean the first bit, whatever's in the middle there.
Yes.
So
again, these two are the same, right? Because this is the bisector of A. Yes. This is also clear.
all this stuff is all this stuff is great.
We take the perpendicular now. Right, perpendicular. Okay, so AOX equals AOY. I forgot to put here Y X. Right, so AOX equals AOY because angle X IO equals YIO and AO equals AO. This we good, yeah, David? So that means we have these two equals the XO equals OY. So we are good till now?
Yeah, all this stuff is fine.
Okay, and this one is also equals to this one.
Yeah, also
of the
totally fine.
congruence.
And now for the next step, that's the part that
Yes. The next step, this, right?
Wait, but why do they intersect?
Hypotenuse and leg, hypotenuse and leg. So that means same hypotenuse, same leg, same leg. So
Yeah, but wait,
congruence.
how do we know that line XO and YO intersect at the same point that line MO does? Like how, like that's a triple point.
No. So I took O. O is just the intersection of AO and MO. From O, so from O, I took the perpendicular to AB and AC. So that's how I constructed it. I took the perpendicular directly to AB and AC. This is not OY is not the perpendicular bisector of AC. It's just the perpendicular from O to AC.
Okay.
But there's okay, so yes, you can use this to prove finally the last two triangles are equal to each other. But this is
Yes.
where it gets interesting because you can even clearly see from the diagram that like this angle MOB and MOC,
Yes.
when you add those, like those are supposed to be the same angle, each of them, because it's perpendicular.
Perpendicular
same
bisector, yes.
etc. Yep. And then you can literally see that what is it? AOY and AOX. It's not like this the AO line meets the OM line in a straight line, right?
Yes, it kind of meets here, to be honest, but then this triangle would be hard to
Yeah, but I
draw.
mean, like those perpendiculars do not meet the perpendicular between M. Like, there's not actually a straight line between A and M, which means just logically from that drawing, you can see that the angle BOX and COY cannot be equal to each other. Otherwise, yeah, the angles
Yes,
are
they
according to our
cannot
logic,
be.
they're supposed to be.
Yes.
But they shouldn't be. Like, there's
Yeah,
just no.
they shouldn't be. Yes, they clearly look like yeah. But where is the flaw, David? Like, why aren't they the same? Because I have no flaw technically, right? In this proof.
Actually, if you move A, right, like in theory, like you see the point A, if you move it.
Move it right here.
Yeah, so what happens is that I guess the line that starts from M.
So like this.
Yeah, I mean, if you move it a lot, actually, like not just like this much, but
Okay.
if you move it like much more, right?
Let's move it. Let's say here. What do you say?
What's gonna happen is that it's not gonna, because here, like in your drawing, it all like it intersects very closely to the outside of the triangle. But if we move it, for example, in this drawing that you're doing right now, the intersect outside. Like if I take like a ruler or
Are
whatever
you
and put it
sure?
on the screen.
Are you sure?
Yeah, yeah. Like right now you're you're putting it like a bit too closely, but the angles like really in your drawing even don't look like they are equal. So you see, like even here in your drawing, like they're gonna intersect outside. So
Okay, sure.
That's weird to me, no? Like to me, if you move A, you can make it intersect inside or
Yes,
outside.
you can, but aren't there like triangles
And
where
the intersect inside if the triangle is actually isosceles, right? And if it's not, then they're gonna
that's a
intersect
strong
outside.
claim. That is a strong claim.
I mean, I don't know, but
'cause,
I'm just, at least from your drawing, because we're basing all this on the drawing, right? So
Yes.
if we base everything on the drawing, then we're gonna get the drawing to get us to do anything we want. So yeah, I mean, where's the proof that actually everything intersects inside? Like, I did not get that yet.
Yeah, me too.
I still don't understand like why and what proved this. Like, and to me, it's really the first step. Like,
so you say that you
I mean,
say
it
that
doesn't. You can draw one right now. So if you make the side AB much smaller than BC and AC, it will intersect
yes,
outside.
I'm not
yeah,
saying that
exactly. That's what I'm saying, right?
I'm not saying that it always intersects inside, right? But for some cases, it does intersect inside, right?
Yeah, but we want all the cases to intersect inside, right? Isn't that what the
Yes.
proof is based on?
It's true. It's true.
Which means that if it's only a special case, then it means that it's only for actual isosceles triangles, which means for the rest it does not work. No.
So can you
Because
prove
get,
that?
like, I mean, maybe it works, but like you need to be in special conditions, because I mean, you can probably draw like similar triangles even if it intersects outside, where you get the same conditions, right? But it probably does not work in all cases. So
Yes.
I don't think the fact that it intersects outside is actually the only point. There's probably another point that makes this wrong, but I think it's part of it.
I see.
Yeah,
Okay,
so it
so
is a problem.
I
Yeah, so because, okay, so like if you draw it with it intersecting outside, then the step where you go from AX to XB and assume that that entire length is the side of the triangle no longer holds, because then you have a dashed line that comes out and you're showing that there's actually a different triangle that is larger than it, that satisfies this isosceles principle, but not this one.
Yeah, that is correct. Join. Okay, so
Yeah,
I think
but
it's
I
time
think there
to.
might probably be cases where actually you can still get this to work even outside, but only for wait, let's see.
I think it's time to like divulge the answer.
hold
Right,
on,
so-
give me one more chance. So if this, if the triangle is isosceles and you continue the AO line until it intersects with BC, then it should split it in half, which is basically what OM does. And that
I mean,
means either,
on this particular drawing, not really, right? Because I mean, if we do this, it's gonna meet like here, so like this.
yeah, but it
still-
means that new intersection point, which let's call it N, then it means that N and M are the same point.
Why?
Because for the isosceles triangle, the
Yes, yes.
bisector and yeah, the perpendicular
I
are
mean,
the same.
technically, Bagrat, I mean, if every triangle is isosceles, that means every triangle is actually equilateral. So, because you can do the same thing
Yeah.
here, right? With, so you can also prove BC equals AC if you just take this intersection, right? Like this one and this one, right? Something like this. If you take you're gonna also prove that AC equals BC. So what you're saying is just a consequence of what we proved. It's not really the flow. Okay, so there is an interesting lemma here that debated a lot of people. So after the point that we convince you that O is inside, it's basically over. Like there are not other flows. So that particular intersection happens inside if and only if AB equals AC. That's basically it.
Yeah,
If it's not, then it's outside. And yes,
yeah.
you did get you did get the right answer. I was just trying to prolong it just to make you try to doubt yourselves.
And you were teasing us. I know it.
And it's not even an intersection. It's basically the whole intersection is the whole line itself.
Yeah. So the trick when debating people with this is taking like an approximate isosceles triangle, so that by the inaccuracies of drawing this, it lies inside, and you make them question, because everything after that is correct. Like all these congruents are fine.
Yeah.
So that's basically, so in the Olympiad there was a problem, prove that the intersection happens if the triangle is isosceles. So what will you do is take a random triangle like this, put the intersection inside the triangle, and prove this contradiction. That's actually isosceles. So it's a contradiction. That means this, the statement that's inside is wrong. So that's what we do. Yes, but again, it's a very nice debate, to be honest. It takes some time. I was also explain this one time, and well, I did not get it at first, but it did become clear afterwards. Yeah, and I guess that basically concludes the session. If you guys are curious, yeah, this is, to be honest, some basic stuff. But if you are curious, I can show you guys like the strongest problem that I proposed, like to a competition, which I think it's like yeah, it's this one. Okay, I can put it inside. Of course, I'm not gonna hit you with this, but that's how it looks, and that's basically the proof. I guess I can put it inside if I can put it in core. I guess if you are curious about it, to read it more. That's basically the problem that I proposed when I was at my peak. I guess I put it in core if somebody's curious, like to read it in full. And yeah, that's basically it, David. I guess you can.